Welcome back to our news report for this week's lab. As an introduction, we analyzed glider's movement on an air track to study motion. A glider basically was able to float on a frictionless surface due to the air track's wheel having holes where air was blown from downward. And we were also able to visualize another position versus time graph using our software. We also the graph that we replicated showed a linear and constant velocity where our direction actually changed twice. And with our calculations, based on our data, we were able to show the numbers that we got for velocity and percent difference. And also, we made a prediction on how the shape of a specific graph that you will later on see will look like if the y-axis values were different and varied. So some of the literature tells us, specifically this review, can really help us understand this tool. Really the main key point in the air track is that it creates a friction-free surface, and we can use it to study basic concepts within kinematics, like of course velocity, acceleration, momentum collisions, kinetic energy can all be collectively studied. And the study also kind of shows students how they can further explore these ideas, which of course we will most likely see in future labs. So the closest thing that I could find that could be used as a real life reference to what we sort of like the procedures that we did, and some of course the apparatus that we used, is this knee glider. So physical therapists can actually use this rehabilitation tool, for patients who may have suffered an injury or they had surgery. This can help them regain some range of motion. And really, essentially, it's basically a smooth track with this movable carriage near their foot. And we can really look back to the air track glider because, of course, frictionless motion. And, keeping in mind Newton's second law, force equals mass times acceleration, and how, more force can make the leg move faster. Of course, highlighting velocity. And the knee glider actually makes it easier to move the leg more smoothly because it relies on a friction, not a frictionless, but a very low friction surface. And of course, as we saw, the air tracker glider, its frictionless surface was thanks to the air, and it was able to show us how force affects motion.
For this lab, it was very similar, or we built on what we had learned in the previous lab, lab one. So for this one, we're still using the same materials, with just an additional air track. To do the procedure, we gathered all our supplies, made sure to log into the computer, turned on the sensor, recalibrated it, made sure it was aligned to the air track. So like this is like the air track and the sensor were like facing each other directly, not like misaligned at any point. We also made sure that someone would keep the glider at 0 or right in front of the sensor before we were calibrated, so that way when we did run the test, we would get the most accurate results. We tried to make sure that our air track and our sensor was either together or in a place so that way it wasn't wobbling or moving around. It did take us quite a few times to get the graph exactly how we wanted it. We ended up using a section of like our fourth graph, and that was what we used to create our velocity time graph and then base our tables on. And overall, we did get very similar scores to it. Again, once we turned on the computer, we logged into Capstone. We opened up the program, got it ready for the position versus time graph, which was the first thing we recorded. Um, Once everything was calibrated, we went ahead and let go of the glider so that way it could start moving and the sensor could start picking it up. Again, it did take quite a few tries. At first, it wasn't reading anything, and then it was reading everything, and then too many spikes and things like that. So we had to calibrate. We would move around the sensor. Um, all in all, we were able to finally get a section from our fourth try that was appropriate and not bumpy or no major issues with it. And using that one, we were able to continue our lab and finished our tables, find our velocity time graph, and then finish the tables for our velocity and get the percentage difference or the error. All in all, this procedure helped us better understand and tie in together what we had learned previous lab about how the sensor works and how the slope of the position versus time graph can change, depending, of course, again on the velocity and the direction in which it's going. Um, this is part of our data and data analysis for Lab 2. This is our graph. This is the first thing we did once we completed our procedure. It did take quite a couple tries for exact, and then from there, it was only a section of the fourth graph that we used to create this. Following our first step, we created our first table, which was the key points of the graph. So everything we had annotated previously on the graph in the slide before, we wrote it down into a table so that way we could have all the information condensed there to better assist us in the following steps. So for this one, it's following the same key. So the initial position was A, and that time was 29.35 seconds. Position was 0.05 meters. Changing direction, B, was 32.7 seconds, and then the position was 1.70 meters. The second change in direction, or the B with the little yellow asterisk, was 36.7 times seconds, and then 0.02 meters as a position. And then the final position, C, was 39.2 seconds, and the position was 1.01 meters. So all of that information came from our first position, or from our first slide of the position versus time graph. That position versus time graph, again, we had to use a specific section from our fourth try. So that's why the times do have later times rather than just, oh, first second, second second, third second, fourth second. But our second step, following our first step, was our second step was then to use. So for our graph prediction, this is our second step was then to use the information that we got from our first table that was based on our graph to create our velocity calculations. So again, velocity is just the final position minus the initial position over the final time minus the initial time. So that's what we did. For each line, again, it went from A to B, B to B with the yellow asterisk, and B to yellow asterisk to C. So for line A to B, it was the change in position 1.65, change in time was 3.35. So our overall velocity was 0.49, which is what we calculated. The line from B to B with the yellow asterisk, our second B, was negative 1.68, and that was our change in position. And then the change in time was 4 seconds. So our velocity for that one was negative 0.42, which checks out because for at B to second B, it is a downward going slope. So it was from the position A, it was going upward. And then from there, it went downward. So it does agree with the whole negative position. Negative velocity means it's going down and the slope is going down. From there, yellow B or the asterisk B to C, which was our final position, was the change in position 0.99, and then the change in time was 2.5 seconds. So our overall velocity that we got was 0.4. All our velocities, we calculated them, and we also kept significant figures. So it was two significant figures, and we rounded up. So for our graph prediction, this is what we thought it would look like once we put our position versus time graph into a velocity versus time graph. So we thought it would be positive because it was in the position versus time graph, it was going up. So we thought it would be positive above the zero axis, and it'd be going constant because it's a constant velocity. From there, where it changed directions, it would go straight down and then be again constant velocity, but just in a negative form. And then from there, again, it would shoot up from the change of directions from yellow asterisk B to C. It would be again going positive. So again, it would be above the zero axis or the x axis, and again, being going constant velocity. So that's how we got it to look like a V, more or less. We also addressed the questions from our lab, how the line would look if we increase our y-axis. So if we increase our y-axis, that means our slope is. From there, we moved on to creating our velocity versus time graph that the computer generated for us, which is right here. You can see it does follow more or less how we thought it was going to be, with the positive, flat, constant velocity, then the decrease down to the negative velocity, then the increase again back to a positive velocity, and how we cut it off there. But it continues in that general motion as the graph continues. We can see that once we highlighted, we could see like the mean depending on the position. So like the first flat would be from A to B, second flat, the negative one would be B to the yellow asterisk B, and then from there it would be the yellow asterisk B to C, which is the next positive plateau. So that's how we got. Again, step 4 and 5 was just seeing the velocities and comparing it to the velocities that we had gotten prior. So our first velocity was 0.52, which was what the computer gave us. Second was negative 0.43, which is concurrent because it's going down, and then again it increases to 0.38. So that just shows it does increase, but it does increase to the same velocity that had it started with, because again, as it continues going up and down and up and down, it loses its velocity. So after we had created a position versus time graph,
In this lab, we learned how to analyze motion through hands-on experience by creating position versus time graphs. We also took a look at velocity versus time graphs. We used a glider on an air track, a position sensor, and observed changes in slope to demonstrate this motion. From there, we also identified key points like initial position, turning point, and final position, and we used that to calculate velocity. We also compared it to the actual values we got from the program, and we calculated the percent differences, which indicated how accurate we were and our equipment limitations. We did encounter issues with our sensor, and also when we looked at our velocity graph, our position versus time graph looked fine, but it was very bumpy, so we had to do a lot of reruns. And we also forgot to annotate, so we had to create our graph all over again. And overall, this lab reinforced how motion can be used to describe one dimensional kinematics and how slope connects to position and time, and how these results can be interpreted. Thank you.